Hello everyone, welcome back. So in this video we are going to learn about the next modulation scheme in amplitude modulation, that is single sideband modulation. Okay, so in short we'll call it as SSB, or we'll also call it as SSB SC. Okay, so all these are same. Single sideband modulation or single sideband suppressed carrier modulation is also same. So the main basis for this single sideband modulation is, so we have seen in DSBSC modulation the spectrum of the DSBSC model. Let me draw it again. So this is the spectrum of so this is the spectrum of DSBSC modulated signal. So this is FC, this is FC plus W, and this is FC minus W, and this is minus FC plus W, and this is minus FC minus W. So if you observe here, this is upper sideband and this is lower sideband. If you observe here, both the sidebands are replica of each other. So both the sidebands are replica of each other about the carrier frequency. So both the sidebands are replica of each other about the carrier frequency FC. Okay, so if we can suppress one sideband, if we can suppress one sideband and transmit, if we can suppress one of the sideband of the message signal and transmit, then the other sideband can be reproduced comfortably at the receiving end. Okay, because they are replica of each other, so receiving end. Okay, so we can transmit only upper sideband, or we can transmit either lower sideband. If one of the sideband can be transmitted, if we can suppress one of the sideband and transmit so that both are replica of each other, the other can be easily reproduced at the receiving end. Okay, just the reproduction only. So we can just take the mirror image and we can easily reproduce the other. Okay, so by doing by suppressing this one of the sideband, the bandwidth and the power required to transmit, for new modulation technique becomes 50%, that is becomes half when compared to DSBSC. Yes or no? So when compared to DSBC, now we are transmitting only one of the sidebands. So suppose if you transmit only upper sideband, so only frequencies up to FC is present, FC to FC plus W, so only this part is present. Okay, so the maximum frequency bandwidth is equal to, maximum frequency is FC plus W and minus the lower frequency is FC. Now if you transmit only upper sideband, if you assume, so this is minus FC, so minus FC plus FC gets cancelled, so bandwidth is equal to W. So in the case of DSBSC, bandwidth is equal to 2W, so bandwidth is decreased by half. Yes or no? Similarly, the total power is also equal to power of LSB plus power of USB. Now we are suppressing one of the sideband, so power also decreases by half. Okay, so bandwidth and power required for the new modulation scheme becomes half when compared to DSBSC. So this idea or this fact, because it is replica of each other at the carrier frequency, both the sidebands are replica of each other about the carrier frequency. So if you suppress one of the sidebands, then bandwidth and power required to transmit the signal becomes half. Okay, so power can be saved and bandwidth can also be saved. Okay, so this fact gave rise to new modulation scheme new modulation scheme, and that scheme is called as single sideband suppressed carrier modulation scheme. Okay, so this is the idea behind this invention. Okay, this invention of the new modulation scheme, SSB-SC. Okay, so next we'll see the time domain equation of SSB signal. So DSB-SC signal, so it is again obtained from DSB-SC only by suppressing one of the sideband in DSB-SC. Okay, so S of t of DSB-SC is given by AC AM by 2 into cos of 2 pi FC plus FM into t plus cos 2 pi FC minus FM into t. Okay, so this is upper sideband and this is lower sideband. So both sidebands are present in DSB-SC. Now if you want to write the time domain equation for SSB with USB transmission, so only USB term is present, LSB is going to be suppressed. So LSB term will not present in USB. So AC AM by 2 into cos 2 pi FC plus FM into t. That's all. Okay. Similarly, if you want to write for SSB with LSB transmission and USB is going to be suppressed, so AC AM by 2 into cos 2 pi FC minus FM into t. That's all. Okay, so these two are single tone SSB time domain equations. Okay, so once you have time domain equations, what can we find? Power. Okay, so we can find power. So total power in SSB. So total power in SSB modulation scheme. Only one cosine term is present, and this is the maximum value, that is ACAM by 2. So first of all, from maximum value, I am finding the RMS value, maximum value by root 2, and taking square of that. So this becomes AC square AM square by 8. So this also can be written as AC square mu square by 8. Okay, so this is the power present in the SSB signal. So this is the total power, and since we are transmitting only sidebands and total power is utilized in transmitting sidebands only, efficiency is always equal to 100%, both in the case of DSB and also in the case of SSB. Efficiency is 100%. Okay, so this is power and this is efficiency, and this is time domain equation from DSB-SC. Again, it's not a new concept, it is again a derived concept. Okay, so now we'll see the time domain equation for generalized case. So S of t of SSB. Okay, now I will take USB equation now. So it is equal to AC AM by 2 into cos. So this is cos of A plus B form. Okay, so cos of A plus B form. So how can we write? Cos A cos B minus sin A sin B. So cos of 2 pi FCT into cos 2 pi FM into T minus AC AM by 2, because it is multiplied by all the terms, into sin 2 pi FCT into sin 2 pi FM into T. Okay, so cos of A plus B form. So this one is cos of A plus B form. So cos A cos B minus sin A sin B I have written. Okay, so this is now AC by 2 into AM cos 2 pi FM into T into cos 2 pi FCT minus AC by 2 into AM sin 2 pi FM into T into sin 2 pi FC into T. Right, so what is AM into cos 2 pi FM T? So in singleton case it is M of T, so this is represented by M of T. In the generalized case this is represented by M of T. AC by 2 M of T into cos 2 pi FC into T minus AC by 2 into, so what is this? This is 90 degrees phase shifted version of M of T. So M of t, its 90 degrees phase shifted version is given by Hilbert transform. Okay, Hilbert transform, and it is represented by M cap of t. Okay, so we'll learn about Hilbert transform in signals and systems topic. So there I'll explain you very clearly, but as of now please remember that M of t 90 degrees phase shifted version is Hilbert transform. It is represented by M cap of t. So this is represented by M cap of t. Okay, M cap of t is the Hilbert transform of M of t, that is Am cos 2 pi fm t. 90 degrees is Am sin 2 pi fm into t into sin 2 pi fc into t. So minus sign is for upper sideband, and if you derive the same formula for lower sideband, it will become plus, because cos of a minus b is cos a cos b plus sin a sin b. Okay, so minus. So this is the generalized equation for SSB. Okay, so this is generalized equation for SS, generalized time domain equation for SSB signal. Okay, so this minus is for upper sideband and this plus is for lower sideband. Okay, so this is the generalized time domain equation for a given SSB modulated signal. Okay, so now if you draw the spectrum of SSB signal, so if you draw the spectrum of SSB signal S of f with USB transmission, also I'll draw the spectrum of S of f with LSB transmission as well. So S of s with LSB transmission. So with USB transmission, this will be the spectrum. Only upper sideband is going to be transmitted, Fc plus W. So on the negative axis also you'll have this. So minus Fc minus minus W. So this will be the spectrum of upper sideband. Okay, so spectrum of SSB with upper sideband transmission. So similarly, if you draw the spectrum of SSB with the lower sideband, only lower sideband is going to be transmitted. So only lower sideband is present, Fc, and what is this? Fc minus W. And similarly here also, so this is minus Fc, this is minus Fc plus W. Okay, so in both the cases, if you find the bandwidth here, so what is the bandwidth here? So bandwidth is equal to highest frequency is Fc plus W minus lowest frequency is Fc, so which is equal to W. And here also bandwidth is equal to, so what is the highest frequency? Fc minus the lowest frequency is Fc minus W, so this becomes Fc minus Fc plus W, so which is again equal to W. So the important point here to be noted is the bandwidth of SSB modulated signal, single sideband modulated signal is equal to the message signal bandwidth, is equal to the message signal bandwidth. Okay, so in the case of AM and DSBSC, we have got bandwidth is twice the message signal bandwidth, but in the case of SSB it is equal to the message signal bandwidth. This is very important point which you have to remember. Okay.